Okay. Well, thanks for coming today. I'm Rob Futrick. I'm the CTO here at Cycle Computing, and I'm going to talk to you about why would you not use public cloud for your big compute and big data problems. And so basically, at Cycle Computing, we kind of have a fundamental belief that access to compute creates new science and enables people to answer new questions, harder questions, and basically pushes the state of the art and helps advance everything for everybody. And given recent advances in cloud, we are firm believers that the cloud is the way to enable compute for users. And so that drives our mission here, which is making compute scalable in the cloud, productive in the cloud at any scale. And that goes from 32 cores to 3,200 cores to 32,000 and up. Any scale, access to compute is a good thing. So we obviously talk to a lot of enterprises. We talk to a lot of different users in a lot of different places. And some of them are using cloud already, some of them are looking at it, and some of them have written it off, at least for now. And these are a few of the reasons that we hear. Often we hear, well, I already own the infrastructure, so I don't need to use the cloud. The cloud's too expensive. It's going to cost us way too much. Security in the cloud, we're just not comfortable with our data going over a public internet and our data residing in someone else's data center. Or we have data inertia. We have such large data sets inside already. There's no possible way that we could use that in the cloud or use some kind of hybrid strategy where we're using the cloud to supplement internal resources. Or sometimes they say, look, we have custom hardware. We have a custom workflow. We run MPI jobs. We need low latency interconnects, or we need access to GPUs or some other kind of capabilities that they don't trust the cloud providers to have or to have in enough scale. And then finally, not so much nowadays, but definitely a common refrain we used to hear was that the cloud is just too hard. They're having enough trouble with their own internal data centers. They don't need to complicate the workflow. And often we'd hear these from three basic perspectives. So you have the end users, you have the scientists and the engineers, and then you have the system architects, and finally you have organizational concerns. And the end user is someone who's just trying to get their work done, and that's their main concern. And in the cloud, it's trivial to get a server. It's trivial to get a decent number of servers. There are even open source packages that'll facilitate starting cores. But as we like to say, starting cores is the beginning of the problem. And it's a fun problem to solve, so a lot of people like to look at that. But then the hard part of actually getting a workflow up and running is often too daunting for the individual end user. They're too busy with their science, with their risk modeling and other work to worry about onboarding their entire workflow. And then the end user, they have to get their data in the right place at the right time, and that can be a challenge to them, especially again, they're already busy with their other work. They don't need to add yet another set of tooling. And learning to exploit unlimited compute is an interesting one. That's something that people often don't realize that they have, a problem that they have. But basically, if you're used to taking advantage of the compute that you have, often you'll find yourself tailoring the problems that you're trying to solve and the time frames that you're trying to solve them in to the environment in which you've essentially been working. So if you have access to 1,000 cores internally, you'll start building a mental box in which those are the kinds of problems that you ask. So learning to kind of retrain yourself to take advantage of zero queue times and unlimited scalability is really something that requires some work. And then finally, understanding your costs. You can't. The cloud can be incredibly cheap, as we'll talk about, but you still need to know how much you're spending, and you still need to know are you within your budget. You don't want to have a nasty surprise at the end of the month. Then you come to the system admin's perspective. So the individual users have their workflow to worry about. But you can often have multiple environments. You have many users that you're supporting, that you're enabling in the cloud. And so you have to concern yourself with all the different workflows that are going on. You are trying to facilitate the science that your end users are doing, or the risk modeling or design work, et cetera. So your concerns are broader than just a single application or a single workflow. And then as with the end user, you have to manage data placement and you have to manage data access, and so security concerns come in there. And then, as I mentioned, with many users, that means multiple software suites, multiple workflows. And then once you are trying to provide this compute, you need to work on managing it, you need to simplify access, you basically make your own life easier in supporting your end users. And then you want to grow that across your organization. And then the same mindset shift in terms of exploiting disposable and unlimited resources, but across cloud providers and even within a single cloud provider. And then across the world, the different regions, the different zones that people offer compute. And then finally, you have the organizational perspective, which is, again, security. You need to make sure that only you are accessing your data, that you can trust that your validated environments, that your regulated environments are going to hold up in the cloud, and that the expenses and budgeting that you are going to incur are forecastable and measurable, and again, no nasty surprises. You're going to want to manage and optimize your workflows across cloud providers and even within a single cloud provider. And then finally, we see most companies as utilizing a hybrid strategy. People have infrastructure that they want to use, and some of the cheapest cores are the ones you already own. And so supplementing that efficiently and easily is a big concern. And this does not matter, or this doesn't change whether you have an HPC workload or a big data workload, or you name your kind of buzzword of choice. You have your classic HPC problems, which can kind of be thought of as small data creating big data. And you have your new kind of workflows, analytics workflows and others that is big data creating small data. But the concerns are the same. You're still using compute resources, and you still have to solve all of those problems. So given that kind of the difficulty I just outlined, who is actually using public cloud for all their big data workflows and for all of their HPC workflows? And it's pretty much everyone. So the customers that we interact with are in finance, risk modeling, pricing, quantitative finance, et cetera. Then you have your big data customers or big data problems, people with data lakes, huge Cassandra clusters, MongoDB, and all Hadoop and Spark. Name your tool set of choice. Life sciences is huge in the cloud. Everything from genomics to proteomics to molecular modeling, comp chem, you name it. And then finally, manufacturing, oil and gas, simulation. A lot of people write those off as traditional MPI problems. You're doing computational fluid dynamics, but a lot of people are solving those workflows in the cloud efficiently and at scale. But we're here to talk about one specific use case, which is the Broad Institute. Their cancer program had some researchers that had a problem their internal infrastructure was not sufficient for. They basically wanted to run machine learning. They were going to use machine learning to help direct the cancer research. The traditional methods they were using were essentially brute force and were just requiring too much compute. They needed a smarter way to look for solutions. They had hundreds of cancer cell lines. These cancer cell lines had information on genetic mutations that lead to cancer and other problems. They needed to cross-reference them and create kind of these maps among the cell lines. And each one of those data sets was complex in and of itself, let alone kind of the combinatorial explosion that you get when you start mapping them. So their internal infrastructure was just not sufficient. Running these maps for just a couple hundred samples on a single CPU was decades of computing, so it was completely infeasible. Their internal process just wasn't able to handle scaling this. And if they had stopped all of their work, if they had taken advantage of the full infrastructure they had, it may have been sufficient, but that kind of coordination across the organization was not going to happen. It's too complex. So they came to us and came up with a cloud-only workflow. So I had mentioned hybrid and burst earlier. This one is cloud-only. They were actually going to run in the Google Compute platform. And they had their internal storage that contained these cell lines and other data they needed. They exposed that data via a RESTful API that our workflow in the cloud was able to use to pull the data into the cloud. Now they used Google Cloud Storage to initialize the system. They pulled the data into there, and then it was kind of a traditional batch system for the actual execution. And they used Univa Grid Engine, for those of you familiar with batch schedulers, as the resource manager and task distribution. Now, one thing I want to note here is that in order to make this cost effective, they took advantage of Google's preemptible instances, which they cost up to 70% less than the on-demand instances. And they last up to 24 hours. If you're familiar with AWS Spot Market, they're very similar. It's basically a way of taking advantage of excess capacity in the cloud provider. The drawback is that you might lose these instances at any time, and so your workflow has to be amenable to that. The Broad workflow was extremely amenable to interruption and restarting. And so these were a perfect fit and allowed them to drop the cost tremendously, as we'll get to. So what were the requirements for this environment? Well, it was pretty straightforward. They had one core per job. We had a lot of control over how we defined the workflow to make it cloud friendly. And the memory per job was about 5 gigabytes, which just limited the instance types we could use, but Google's capacity was well more than enough for our needs. I happened to use Ubuntu 12. It was internal software. It was written in R, which helps remove licensing constraints, which is something that we can talk about offline. And it was a scatter-gather job, or a diamond DAG, for those of you depending on your perspective, which basically meant there was an initial job which set up the entire environment, and then a final step that gathered all the data and produced the final results. Now, as far as storage goes, each job was 200 megabytes, but it was not, that I think it worked out to be about 65 terabytes, but a lot of the data was shared, so it was a smaller data set, but still in the multiple terabytes. And basically, the end user kicked off the run. We uploaded the data to the cloud. Our software at Cycle provisioned the entire environment, installed the software, automated the entire process, allowed the user to not only submit the work into the environment, but manage the entire workflow as it executed and then pulled back the results. And it took care of things like encryption and managing the data for the end user. So as far as they were concerned, it was push button. They just said go. The entire thing ran, and when it was done, our software shut down the entire environment. And this is not a one and done system. This is an ongoing solution for this user that allows them to basically take advantage of cloud resources when they need them. Here's an example from the dashboard that shows the total core count as it grew over time. You can see the timeline down there over several hours as the cluster went from nothing all the way up to 51,000 cores. And then as the jobs finished executing, it scaled back down. And another dashboard of the workflow running, and you can see kind of the split among the work. A little bit of a heat map for CPU usage for more of an admin perspective, but the user was interested to see just how efficiently they were loading down the system. And then they have the final metrics. So it was about 15,000 total instance hours, 243,000 core hours, and 340,000 jobs for the final tally. You can see at total cores at peak was just shy of 51,200, and that was just shy of 3,200 instances. So there were 3,200 separate computers or VMs running in GCP that produced all this work. But here's the most important part. The total price was less than $5,000. So they were able to get access to a fairly massive system for what the researcher could have put on his credit card. And this ended up being about 3 decades of computing on the infrastructure he had at the time. And it took a little bit less than 6 hours, and again, less than $5,000 in total cost. Gave him 340,000 jobs processed across 51,000 cores. And from the time that he realized he had this problem that was not going to be solved internally, working with us and working with Google, it was less than 2 weeks from I need to solve this problem to I have my results. And part of that time was training the user in terms of how to use everything. So the ongoing solution is even quicker. This is a repeatable process moving forward for them to supplement internal capacity. And that was just one use case. Of all the industries I talked about earlier, the Broad is just a particular life science case that has this need for scale. But there are many, many others. We've talked about many before. So I started off saying, why not use the cloud for your big compute, big data workflows? I mentioned the reasons already. They already own the infrastructure. It's too expensive. Security is a concern. Data inertia, customized workflows, or it's too complex. And as we showed through, I think, the Broad use case, all of those are addressed. So they had infrastructure. It wasn't sufficient. It was already being used by other users. The cost, well, the whole run cost less than $5,000. That's just that is a whole new level of compute at a whole new low price point. Security, our software took care of encryption, our software took care of all the kind of data transit, and then the big cloud providers, they deal with security at a scale that very few people have to deal with, and they have teams that are dedicated to that. So it's a level of expertise that is hard to replicate. So now, why would you use the cloud? What was the benefits to the Broad and other organizations that we work with once they've overcome all those problems? Well, the users have zero queue time. They have access to as much compute as they want, as fast as they can get it. It's very simple access, it just works. And on top of that, the time that the end users used to spend on IT concerns, on writing scripts, on managing workflows, on bringing up infrastructure, bringing it down, or internally dealing with segmenting their workflows from other users on the same shared infrastructure is gone. Users are now focused on the science, they're focused on the quantitative finance, they're focused on the design, as opposed to having to kind of split their focus. From the sysadmin's perspective, they've now enabled their users to access compute with zero queue time, but they can control that access and link it programmatically into internal workflows. The same perspective of not having to focus on the wrong tasks. Their IT people no longer have to focus on pulling drives and checking network cables and making sure the IB interface is operating at peak efficiency. They can now focus on the IT concerns of the workflows of their users. So it's a huge win for efficiency and value. And they can manage the user's cloud experience, and they can manage the compute that they're giving from a central location, and then data management kind of comes along with the workflow management. And from an organizational perspective, you actually have, in some ways, a more secure environment. You can match your budgets to the actual work being done. So you can directly map back the cost of a run to the researchers that ran it and get a better match between the value of the run and the work being performed. Your on-demand capacity is an operating expense. It's no longer an investment in infrastructure that you're going to be depreciating over time. It's not something you have to worry about using and keeping running and keeping full. It's on demand. And you can take advantage of the latest tech. Very few people are going to upgrade their infrastructure as fast as the major cloud providers. Very few people are going to have access to the scale and kind of the next generation technology that the cloud providers have. Your new infrastructure is great when it's new and shiny. 6 months later, it's out of date. But the cloud provider's capacity is not out of date. And finally, you don't have to worry about data center optimization. That's not your business. That's somebody else's business. Let them do that. You focus on the science. You focus on finance. So more and more people are adopting cloud. More and more people are moving their workloads out there and working on some kind of hybrid strategy. There are still some hard problems. So how do you get there? Well, you still have to overcome making the clouds productive. So you can address all those issues, but doing it well, doing it easily, and doing it efficiently is difficult, which is why we're here. That's what Cycle does. Getting back to that original mission of we want to make clouds productive and useful at any scale, that's what we do. So we have software that will help you provision, orchestrate, manage, report, and audit HPC environments across cloud providers, internal, external, et cetera. There are 4 sections to this. So first you have the provisioning of the infrastructure. You want to make sure that when you bring up the environment, it is your environment. You're not just turning the power on, you're turning the power on and then you're customizing the environment. You're setting up the storage, you're setting up the file systems, you're setting up the user's software and the users themselves and every aspect of that environment so that when it's up and running, it is ready to go. Then you have any workflow customization, any tie-ins to the internal environment. You want the users to push a button, and when it's ready, they can start using it easily and simply. Then while it's running, you want to monitor it. You want to have the environment grow and shrink with the work that's actually being done, and you want to be able to track jobs, you want to be able to track errors, you want to be able to automatically recover from anything that happens. If you have an error 1 in every 1,000 boxes, well, that's fine if you only have 10 boxes or 100 boxes. But when you have 10,000 boxes, you have a measurable amount of error that you have to recover from. You do not want to push that onto your end users. And finally, when you're done using it, you want to tear it down. And you want to know who used it. You want to be able to audit that access and audit that usage so that you can then report back on it later. Again, very important in validated environments, regulated environments, and other similar requirements. And that's what we recommend. Thank you.